Thank you. Hear me back there? ¿Se oye? Okay. Good. First, let me run my clock. First, I want to thank the organizers for considering topology a related topic. Thanks to that, I'm being here enjoying this conference. Adolfo's company, and also hearing many things, many new things for me about the nice things that Adolfo has done. They were no surprise to me, of course. I always known he's a very nice guy, but I learned a lot about that. Okay. So here's what I'm going to talk about: topology. I've been studying for many years these concentric quadrics, intersections of concentric quadrics in different kinds, and I will show you how to describe the topology of these intersections for a small number of quadrics, but also for a large number of quadrics if one cannot tell them all. I can say a little bit, rather a big hunch of them. And before going into the topology, I want to prove that the organizing committee was correct, that this is related to geometry, and there are several branches where this guy appears, but I think the most classical is the motion of a rigid body. For the motion of a rigid body in good coordinates, then there are two constants of motion, the energy and the angular momentum. Angular momentum, and if you have two say this is a surface of constant value for the energy, and this is constant value for the angular momentum, then the motion in those coordinates goes around these very nice curves. These are very neat geometric curves. Somehow the curvature and torsion have to combine in a very delicate way to keep inside both ellipsoids. And also very geometric is the application to the motion itself, because the type of motion depends much on how's this intersection. It can be empty, but then it can have this shape. You have two circles always. Then it becomes, when they're tangent again, it becomes this curve, and then there's two circles again going the other way. In YouTube, you can find drawings where you see the intersection of the ellipsoids and the object turning around. That's geometry, no? It's geometry. But only physicists learn that. Okay. And there are, so we always get S1 cross S0. We can describe all the tangentials and even non-concentric intersections. And I'm sure there are examples, I've seen examples of this for more degrees of liberty, more dimensions, but it's hard to find them for hey. It's hard to find them for three constants like that. Nice dynamical systems, important dynamical systems usually don't have three constants of motion. I try to look for them in relativity. Maybe there are intersections of hyperboloids there. No luck, because there are no rigid bodies in relativity. What's rigid for one observer is not rigid for another observer. They appear in the GPS theory. The position of your position is determined by the intersection of several hyperboloids, but not concentric. Anyway, that's mostly classified information. With many, but I mean like three bodies, or yeah, we can have. Yes. Oh, you tell me later. Okay. Yes. Yes, that's what I meant here. Has more than three? Has more than two constants? Okay, well, I'm ready to learn. That's what I'm saying here. Okay, so they also appear in dynamical systems in different forms. There's a certain orbits, spaces of orbits, as invariant manifolds in generalized Hopf bifurcations, and in some theoretical biological examples. I'll give you an example of the first kind. If you have this linear system of equations, well, this is trivial. It's a trivial system. Here you can see the solution. You can write the solutions immediately. And nevertheless, there's a lot of topology and topology hidden there. Here's an example. It's what can I draw in R2, but you have to think we are in Z2, and these are two-dimensional objects. They are all two-dimensional objects, and the axis. Here the question is that there are different behaviors of the orbits. There are these orbits which are in the origin is an orbit, and then there are these orbits along the axis that get close to the origin, have the origin in their closure. And then there are all these other orbits that come down to the axis, and this produces a kind of problems, because this means that the space of orbits, the quotient is not Hausdorff. This sequence accumulates in this point and also in this point. But if you remove this, then you have all these nice orbits, leaves, and it turns the ones that keep their distance from the origin, and then they have the property that in each of them there's just one point that is closest to the origin. So if you draw all these points, you get a very nice picture. It's a cone, and if you intersect this with the unit sphere, you get an intersection of ellipsoids, as I said. So the space of the nice orbits, it's like that. There's also another geometry here hidden, or topology, which is when these are two-dimensional, this is two-dimensional, or in R4, when they approach here, they turn around. I'm drawing here only the moduli, but there are the angles. They turn around, spin around this axis. And the way they spin, it's very important. It turns out that these systems are very rigid. If two are topologically equivalent, they are also linearly equivalent. Okay, so if you write down Lagrange multipliers, it turns out that the set of those points, one in each orbit, satisfy this equation, are given by this equation, and then you add the unit sphere. You can write this in real terms, and it's something like this. So it's the intersection of three ellipsoids. Maybe you don't see the ellipsoids right away. Took me some 30 years to discover them. But if you add a large multiple of this equation to the other equations, you can make them all positive definite, all the forms positive definite. So it is an intersection of ellipsoids. And these guys are called now moment angle manifolds, and carry much topology and geometry. The even dimensional ones give very nice examples of complex manifolds that are not, in general, not symplectic, and then they I should have practice with this. Okay, and there appear in this theory of non-commutative toric varieties, of which I cannot say too much more. And we just proved that the odd-dimensional ones, they all admit contact structures. Which, okay, so I come to the topology. First, I mentioned that any compact differentiable manifold with a stably trivial normal or tangent bundle can be realized as an intersection of quadrics in Rn, not necessarily concentric, and can be an intersection of ellipsoids when it bounds a parallelizable manifolds. So we know more or less which one do and which one don't, which manifolds do, but there are too many of them. Say, just take all the homotopy spheres, so one has to restrict, and that's why we restrict to concentric ones and a small number of them. So we know that in the case of R3, the intersection is either empty or two disjoint copies of the circle when it's transversal. So I'll recall, maybe everybody knows that, how to describe the topology of the intersection of two ellipsoids in any dimension. So we take two ellipsoids in Rn, and then first of all that we can make one of them to be a sphere, a nice change. Then now we subtract, instead of what we did before, we subtract, so we get it's a different Q1, but already let's see. Any intersections of any number of ellipsoids can be written in this way. And then it's well known that the first one can be diagonalized. And we get an algebraic normal form. Then for the third step, it's easy to see that the system is regular, that is, the manifold is smooth, or variety is smooth as a variety, if no of the coefficients are zero. So we can assume there are P of them are positive, Q of them are negative. And now if you have a transfer intersection and it's compact, if you deform it, keeping it compact, then the topology doesn't change, and we can move all the positive ones into one, all the negative ones into -1, and one have this system. So we have to use this. I did something worse. Okay. So you have this system, this normal form, but then you just have to add and subtract, and you get these two equations with independent variables. So what you have, it's a product. It's 1 point in RP with norm 1/2 and a couple of points, each in its space, but of norm 1, and the intersection is then product of spheres. Finish. I have. Sorry. Yeah, they were. Yes, they were. They were always S1 cross S0. No, I did it for any dimension. It's very simple. It's probably well known. I haven't found it written. Okay, finished. Did anyone take the time for this proof? Okay. Let's try now concentric ellipsoids. What's wrong with that? Only that the forms are not positive definite, but let us see. We can always assume one of the ellipsoids is in this form, and then we'll start moving the other ones. The other one. We would like to make the other one diagonal. No, it's not possible in general. Here's an example. This is really like c² = 1 in complex coordinates, and it has two solutions. And for a diagonal case, it has to have S2 crosses a product of spheres, so it can be. We know that it has to be empty, or 4 points S0 for S0 times S0. So this one is definitely not diagonalizable. Well, this is not very bad, because it's, in a certain sense, it's the only problem we have to deal with. That is, there's a way of writing this where all the coefficients, where all the non-diagonal part is a sum of c², and all and the rest is diagonal. I've written it this way. These are the positive ones here. These are the negatives back down here, and I divide the previous ones also into bunches. I call these coefficients AI and this BI. And this is essentially due to Terry Wall, and the idea is that there are also complex parameters involved, but a complex non-zero parameter can always be joined to 1 in the complex, as opposed to the real ones. That's a big difference. Okay, so we only need to care about the diagonal part. Well, the coefficients, now we see when this thing is regular, and it turns out that it's regular when the coefficients that correspond to the positive part below are different from 0. You don't care about the other ones. So it looks simple. But now when we want to deform it to putting all of them in a nice position, but there's a problem. We have non-compact things, and some things can happen at infinity. I don't know if that's clear to you. For example, take a sphere, then you elongate it to an ellipsoid, keep growing until it becomes a cylinder, keeps going and it becomes a hyperboloid, and it's changed its topology, but all the time it's smooth. It is smooth all the time, so you have to look at what's up there. Okay, and then the condition for it to be regular at infinity is this one. You take one of the coefficients in the positive part, and on the negative part, they shouldn't add to 0. And so we have to ask that. That means that every coefficient of this type, A1, determines a negative point minus A minus 1, and you cannot move the B coefficients across one of these, because it would change the topology, and vice versa. This one turns 1. Here's a drawing. The black points are the coefficients. This is A1, 1, A2, 1. And these two you cannot join, because here's a coefficient B something, such that it's negative, doesn't let this one join this one. And the same back here. Clear? Maybe here it's better, bigger, but also you cannot join this coefficient with this coefficient. This one here and one here you cannot join, because the AIs cannot be 0. So you cannot go through here. But also this point and this point cannot be joined, coefficients. This BI minus 1 coefficient, because there's this obstacle which comes from this coefficient up here. So you cannot have this kind of point. I'm denoting the coefficients. The coefficients have two coordinates. If the last coordinate is 1, I call it an A point A. I write it, I say. If the second coordinate is minus 1, I put BI here. So this is the point A1. A1 is this. And the coordinate here is 1. This is A2, 1. This is B1 minus something, B1 minus something, etc. And you cannot have two opposite, two of the one A and one B cannot be opposite. So it's not as simple as before. You have a bigger picture. Here you have many more. But then before, in the case of 2, you just have the positive and the negative ones, and you could do whatever you wanted with them. Now, you cannot join them at will, but there are a lot of obstructions. So what you really get is not a partition of two numbers like before, but a partition in many numbers. Okay. And there's the simplest case would be a Minkowski case with signature n minus 1, 1 or 1 n minus 1. But even those can give problems. Some of them can be done, and then you get you do the algebra again, and you get the product. But very soon you get one that doesn't. You take this system. These two equals these two hyperboloids, then you cannot, there's nothing you can do about it. No matter what operations you make, you wouldn't get separate equations. And this because it's not a product. It's actually a torus with 4 holes that go out to infinity. So this is not a product. So I don't think it's possible just by manipulating the equations to reach this object. And so there's a more complicated combinatorics, but it can be done. But then we have more problems, all coming from the non-compactness, because the cases are more difficult. We have to deal with non-diagonal cases, and then for that I have to use what I did is to have a compactification. If you have an intersection of quadrics, say hyperboloids, then you can construct this one. That is, you homogenize this equation by introducing this new coordinate, and you intersect with the sphere. And then you take the part where the new variable is positive. It's not negative. This can be seen like this. You have the sphere, take the tangent space, you draw your intersection of hyperboloids in that plane, and then with a cone you bring them down to the sphere, and then you take half of it. And that gives you a nice correspondence between the hyperboloid in the boundary going to infinity to the hyperboloid in the sphere. The infinity in the plane corresponds to the equator. So you have to remove that equator. So we get this x hat, which is an intersection of 3 ellipsoids. And then the plus is half of it, and your original x can be identified with the interior of this x half. Okay. So you can get to the hyperboloids by this detour. You have to go to understand 3 ellipsoids in Rn, the half of it, and taking the interiors, that's no problem. Okay. And that takes a lot of work. Give me a week, few hours every day, I'll give you the whole proof. I'll just say the idea. We start with 3 ellipsoids. Now we just there are various steps in the proof. You have to know when it is regular. And it is regular. Now the coefficients are in R2. There's a coefficient. And the condition is that the origin is not in one of the segments. The origin is not in the convex hull of 2 of the points. This is bad. This is singular. This is regular. Before you had the condition was that the origin is not in the convex hull of 1 coefficient. Okay. And then instead of putting them the coefficients into 1 or minus 1, it turns out that you can put them in a circle and inside an odd regular polygon. And that's a normal form. So you have this, in this case you have these 7 points, and then you put any number, positive number of them in each, so you get this partition that reminds you of the previous partition. If you have a triangle, you have just 3 points, and 1 plus and 2 plus and 3, then you can do the high school algebra trick, and you get a product of 3 spheres. But starting from the pentagon and up, it's not a product. And then the other step is constructing the associated convex polytope. You have in the equations for in the homogeneous equations of the ellipsoids, you change the xi square for an ri, and you get a plane, and you intersect it with the unit simplex, and then with first orthon, and then you get here in the first orthon a certain space, which well, the intersection is the intersection is curved, but if you straighten it up by the coordinates Ri, you get a polytope. Very nice, simple polytope, actually. And then you get back the manifold, the intersection, by reflecting this polytope in all the coordinate hyperplanes. Here's an example. Take the simplest partition 1, 1, 1 plus 1 plus 1. Then you have a pentagon in R5 with sides on the coordinate hyperplanes. So you can see how it's constructed. You had a cell decomposition with 32 pentagons, so many edges, so many vertices, and then it is the surface of genus 5. If you reflect only on 4 of them, you get the surface, you get a torus with 4 holes, and the interior of that torus of four holes is the hyperboloid I mentioned before. Okay, if you have more than 2 dimensions, then you don't have this. You cannot use the Euler characteristic, and then you have to do much work, and then you do but essentially the same idea is that from the polytope you can recover you can read inside the polytope how connected it is, what's the homology. The homology splits into several parts related to the combinatorics, and then this is very general. This is true even for any number of ellipsoids, but in our case we have the normal form, and the next step is from this normal form you have to find the homology. The principle is that here in this is the information for everything you need, but these numbers won't give you the information easily. You have to use some inquisitory methods to get the information out of them. Okay, so that takes some time, and then you know the topology, the homology. It's not enough to know the homology to know the variety. Then the way I know that to tell what the manifold is to construct a cobordism. This is kind of a unwritten principle in differential topology. If you want to know a manifold, you'd better look at the cobordism, at another manifold it bounds. A homotopy sphere, no matter how you look at it, it doesn't have any homology or any invariance. But if you have a manifold it bounds, then looking at the manifold you can tell which sphere it is. And then, well, this is the tricks I learned in, well, a graduate student, and then you get the manifold, and then you use some simple geometric tricks, and finally the H-cobordism theorem to get the result. The final result is you can have a product of 3 spheres or a connected sum of products of 2 spheres. The number of summands is the number of points in your polygon, and the DIs are determined by the partition. Okay. For the non-diagonal case, then we have to consider how am I doing with time? Okay. Good. Then the trick is that this is you have one of a diagonal one, and you start adding this kind of things. And when you add one of these things, it turns out that this is a double covering or a sphere branch over the half manifold, previous half manifold. But the trick is to start with the basic cases, do the non-commuted, non-diagonal part first, and then do the other, and then you can get all of them. Then there are cases, particular cases, which don't fit the H-Culbertson theorem, like it's not simply connected or low dimension. You have to do them each one by one. That's the method I've used. Maybe there's a better one, but this is the final result, which I did with my former student Vinicio Gomez Gutierrez. He has appeared before in this talk, and he will appear in the next talk doing geometry. Okay, so so here's the final result. You just get product of spheres, or something's a bit different, like the unitary tangent bundle. You know that you have a sum of complex squares equals 0. You get the tangent bundle of the sphere. It's a particular case. All this can be proved very elementary, and then the connected sums this kind. Okay. Then you have to consider the halves. That's much of the work is done already, but there are cases where you have to look at them. Then instead of having a product of 3 spheres, you have one of your spheres has become a disk. And if when you would do the connected sums of products of spheres, one of the 2 spheres has become a disk, or slightly more complicated spaces. And then finally, I can tell you that the hyperboloids would be the diffeomorphic to the interior of those manifolds. You can specify all the data from the partition. These are not very complicated manifolds. They're just like surfaces, generalizations of surfaces. The first connected sum I showed you is the surface of genus 5. But here we have the result. You have one ellipsoid, it's trivial, it's always the sphere, and there are no hyperboloids. 2 ellipsoids is just like one ellipsoid. One hyperboloid is just as easy as 2 ellipsoids. By the way, I haven't seen anywhere where they do the topology of a hyperboloid, but it's very elementary. And for 2 hyperboloids and 3 ellipsoids, you have this more complicated partition. The number of cases here is 1. Here it grows linearly with n. Here is exponential, it grows exponential. The topology here is trivial, and here it's very simple, but the proof is very elaborate. Actually, one hyperboloid, it's more complicated than 2 ellipsoids, because it's like the half of 2 ellipsoids. And the same here. Actually, and here you have to choose one of the vertices, keep it fixed, otherwise you can rotate them. So it's slightly more complicated. Okay, for a higher number of quadrics, everything seems to go wrong. Mr. Murphy's paradise. There's no reasonable algebraic form. Once you put the 2 equations in a normal form, then you lost all your cards, and then for the rest you cannot change the coefficients. So all those coefficients are invariants, and the number of parameters then grows quadratically with the number of variables. Someone told me that's a characteristic of the wild systems that Jose Antonio was talking about here. These are not algebras, or not yet. Okay, and the regularity condition extends easily for the diagonal ones. For the non-diagonal ones, we have no idea. If you had nice topological normal form for the diagonal ones, that would imply a classification of many polytopes. The experts in polytopes theory, problems that experts in polytope theory don't even mention. They don't say it would be nice, would say it would be very difficult, to say it's very impossible. They just don't mention those combinatorial problems. Everything can be reduced to basic configurations, but what are those basic configurations? One doesn't know. Sometimes I've thought of, now you have in the sphere, say, and you have to put constellations in the sphere that satisfy certain properties. Sometimes I thought of putting electrons and moving them around, but apparently even that is a very difficult question. So in the diagonal case, we have a reduction to a combinatorial problem. That it's impossible problem. In the diagonal case, we don't have even that relation. The homology calculations work out the same, the splitting, but then you can have all kinds of horrible topology here, or beautiful if you're an algebraic topologist. Think of any horrible behavior of the newest generalized cohomology, and then you find one of the intersection that has that behavior. And sometimes it's often. Well, so maybe you just have to start with the simple cases and write a list of up to a certain dimension. And that was around the year 2000, that was the situation. And there came something extremely nice for us, which is the work by Bosio and Mercier, and they studied the topology for any number, and they detected that there's an interesting family of polytopes called dual neighborly. In topology, in polytope theory, there's the concept of neighborly polytopes. They take their duals, and they have the properties of cohomology properties that corresponds to the ones we had considered before. So they conjecture that they would be diffeomorphic to connected sum of sphere products. Something very important happened. There was this work by Barry and Bendersky, Cohen, and Sam Gittler, where they generalized on some other constructions, and it turned out that these constructions include our objects, their generalizations. Actually, we had worked separately into two schools, without knowing each other, but studying the same objects from very different points of view. So we finally joined our points of view, and we were able to prove the Bosio-Merseyman conjecture, and much more. For each polytope, they made the conjecture we get an infinite family. And that was around 2008. 2009. Now we understand what are we doing. The basic configurations we had before are these polygons, and I have the property that you through the line to the origin and one of the points. This divides the others half and half. If you put other numbers here, you don't get that. And then it turns out that those dual neighborly polytopes of any number of coefficients or any number of any dimension and any number of facets, they have satisfied the natural generalization. So it's a generalization of what we get, and then there are many of them. I'll try to to make it more clear this way. You have take a dual neighbor polytope. There's intersections of quadrics that corresponds to that polytope. And Merseyman had conjecture that the complex one, the 2, 2, 2, 2, 2, this one is an intersection of quadrics. It's a connected sum of sphere products. So we proved that the basic one is, and from them that everything we can get from that, putting multiplicities on the original configuration is such a thing. Then in the next dimension, we lost the polytopes, we lost the basic ones, and we go up dimension and you get more and more and more. So it's a lot. The guys in polytope theory say that the neighborly polytopes are most of the polytopes. They feel it's a feeling. Probability or other things. Something went wrong here. And well, there are other operations you can do on the polytopes, like cutting a vertex or things like that preserve connected sums. So there are more branches like this. So it's a good part of the set of diagonal concentric things, and we can also say things about the other dramatis personae in this conference. They have varieties, the hyperboloids, and some cases of diagonal ones. But the difficulty is still in the diagonal case. In the non-diagonal case, we will need to do something. So here's something I have begun to do. How much time I have? 10 minutes. I have to think something fast. Okay, and the differential geometers do something that has always bothered me. They don't speak of the intersections of quadrics, but of the pencils, nets, very British almost, webs of quadrics, which is they take k quadrics. Here we are considering homogeneous quadrics, and well, for them they are complex projective, and they take all the sums of these quadrics. Then this sum determines the intersections of all the members of the family is the intersections of this, and you can change the generators. They look like this. Some of the work I mentioned before part was in the paper by Terry Wall called Pencils of Quadrics. I could have never imagined that it was intersections of quadrics, but it is. Well, I'm coming back to them. So if you consider the family, what they do is study which are the singular quadrics in the family. So they take the determinant, and the hypersurface defined by this in the space of the lambdas, and they look at its zeros. I never thought this would have any interest, but being in that point of where I didn't know what to do, I look back at these things, and what I do is obtain geometric information from this, the number of, I don't know, inflection points or things like that. So I said maybe there's something there, and I just did a little step. If the system is diagonalizable, then all the matrices are diagonal, and then when you add them with coefficients, they're diagonal. So the polynomial is a product of linear factors. So if this singular variety, in that case, the singular variety decomposes is totally reducible, can be reduced to, it's a union of linear things. So there's an obstruction to diagonality, or to being diagonal. And when you do that, the information in this variety, it's a composition, it has all the information about the intersections of quadrics. So if you know this, you can reconstruct the polytope equations, everything. And I don't know if the reciprocal is true or not. Maybe I want it to be false, because if it's false, then I would have other sigmas that are totally reducible, from which I can get all the information about a polytope and another variety. I could get information for these non-diagonal ones, and or you can take partially diagonal ones. In any case, the variety with all its properties, it's an invariant of the intersection, and one has to study what of that information is topological. Something I didn't mention when I constructed the intersection of ellipsoids from the intersection of hyperboloids, I homogenized an equation with an univariable x0, and that variable x0, it's alone. It doesn't mix with the other ones. So that would be a one diagonal. That means that not in the case we studied of two hyperboloids, not all examples of three intersections of three ellipsoids come from hyperboloids. All the purely non-diagonal ones, the sums of complex squares, they are not. So now one has to see. Maybe I don't know. I still don't know. Maybe every intersection of hyperboloids, ellipsoids comes from an intersection of hyperboloids, or not. But maybe that. Well, not every, but how many of them do not come? It's a question that maybe we can read here in this. So let's look like a bit of hope about understanding this big space of non-diagonal ones. I give this talk here, hoping someone has had similar problems and maybe some suggestions about that. And that's all, but it's very recently, last week. But there's also something very recent. I discovered a paper called Linear Systems of Quadrics and Regular Graded Clifford Algebras. It's a very curious paper. It's on some, how do you call it, repository in Kyoto University. It doesn't appear in the author's CV. There's a different version where the systems of quadric don't appear neither in the title nor in the interior. Don't take a picture. I have a present for you. Here it is. So, hey, they were really right, the organizers. How much time do I have? 2 minutes? Eh? 5. 5. I only need one for a last joke. All what I said, it's true also for intersections of superquadrics. Do you know about superquadrics? Well, according to Wikipedia, superquadrics are like quadrics, but instead of exponents 2, you put other exponents, different exponents, like 4, 4, 4, 4, 4. Everything I said, it's true for quadrics of that time. Quartics of that time, they're the same. Coefficient 2 or coefficient 4, you can deform one into the other very easily with a change of coordinates. So I'll write a paper about superquadrics with the help of Adolfo. That's all, thank you. For the linear, yes. Please do. All the ones I know, they're very standard things. No exoticity. No. No. You cannot get homotopy spheres. You cannot get homology spheres, except for one sphere. For the one sphere, one quadric sphere. You cannot get exotic things. What are more interesting from that point of view are the actions. There's the space with the action of C2 to the n. Those are the ones that studied my competitors. The other, they related to Coxeter groups and things like that.
Quasi-homogeneous maybe some quasi-homogeneous one like the quasi-quadrics. You take the same examples and you change some of the exponents. You don't have to change all the exponents.
I'm asking just because in the next talk it's going to appear something,
so it's not like this one. You don't get exotic things here.
Okay.